The system displays a consistent outcome. Response times remain persistently slow across all interactions, regardless of context or urgency. Requests accumulate without clear resolution speed, and delays appear evenly distributed rather than concentrated in specific cases. The observable result is a stable high latency environment where slow response is no longer treated as an exception, but as a baseline condition. A common explanation attributes this to inefficiency or workload pressure within the system. It appears reasonable to assume that operators are overwhelmed, leading to unavoidable delays in processing. Under this view, latency is treated as a byproduct of limited capacity rather than a structural feature. However, this explanation fails to account for the uniformity of delay across varying workloads and conditions. Even when demand fluctuates or capacity is theoretically sufficient, response times do not meaningfully contract. The persistence of delay suggests that workload alone cannot explain the system's behavior. Another interpretation points to coordination issues between different parts of the system. Delays are assumed to emerge from misalignment, handoff friction, or procedural complexity. Yet even when coordination paths are simplified, latency does not collapse, indicating the issue lies elsewhere. The missing element is the absence of attribution within the delay process. No individual operator can be directly linked to a specific delay, and response time is not traceable to a single decision point. This removes the possibility of isolating responsibility for slow handling. At the same time, the system imposes no direct penalty for delayed responses. Operators do not incur measurable costs when response times extend, nor do they receive differentiated consequences based on speed. The incentive landscape, therefore, does not reward faster resolution over slower handling. Within this structure, deferring response becomes a rational strategy. When immediate action carries effort cost but delay carries no traceable consequence, postponement reduces individual workload exposure. Operators begin to shift toward response deferral as a default behavior. As more operators adopt this strategy, response times begin to stretch incrementally. Each deferred action adds marginal delay, which compounds as it interacts with other deferred actions in the system. Latency increases not through a single event, but through distributed, repeated postponement. The system does not signal these delays as anomalies because no individual action appears excessive. Each delay remains within acceptable bounds when viewed in isolation, preventing corrective intervention. This masks the cumulative effect of widespread deferral. A contrast emerges between perceived performance and actual system behavior. On the surface, no operator appears responsible for significant delay, and no single failure point is visible. Beneath that surface, the aggregate effect is a continuous expansion of response time. Attempts to identify bottlenecks fail because the delay is not concentrated. There is no identifiable node where latency originates, only a diffuse pattern of minor postponements. This diffused structure prevents targeted correction and allows delay to persist. As latency becomes more common, expectations within the system begin to shift. Operators adjust their assumptions about normal response time, aligning behavior with the observed average. Delayed response becomes an anticipated condition rather than a deviation. This expectation shift reinforces the initial incentive structure. When slower responses are perceived as normal, there is no pressure to deviate toward faster handling. The absence of urgency further stabilizes deferral behavior. The system gradually transitions from occasional delay to normalized latency. Response time stretches become embedded in operational rhythm, no longer triggering escalation or correction. Delay ceases to be treated as a problem and becomes part of standard operation. A second contrast appears between formal rules and emergent behavior. Formally, the system may require timely responses, but in practice, no mechanism enforces or attributes those requirements. The rule exists without an incentive structure capable of sustaining it. Over time, the accumulation of deferred actions creates a self-reinforcing environment. Each delayed response increases the baseline against which future responses are measured. This baseline drift locks the system into progressively slower performance. Operators entering the system adapt to the existing latency rather than challenging it. They align their behavior with the prevailing response time to minimize effort without incurring cost. This alignment further entrenches the delay pattern. The system's inability to trace delay back to individual actions prevents accountability loops from forming. Without feedback linking behavior to consequence, there is no mechanism to reverse the adaptation. The incentive structure remains unchanged despite deteriorating performance. Eventually, the system stabilizes at a high latency equilibrium. Response delays persist as a structural feature rather than a temporary condition. The outcome reflects a consistent alignment between non-attributable delay and operator behavior. The final state is not the result of deliberate slowdown, but of cumulative, rational adaptations. Each operator acts within the constraints of the system, and their combined behavior produces persistent latency. The equilibrium holds because the incentive structure continues to support it. As latency stabilizes, the system begins to internalize extended response time as an implicit scheduling horizon. Requests are no longer processed relative to their arrival moment, but relative to an already delayed baseline. This shifts the operational clock forward, embedding delay into every subsequent action. Because response timing is not attributable, no corrective signal distinguishes early from late handling. All responses collapse into a single, undifferentiated category of completed, regardless of delay length. This removes temporal resolution from the system, eliminating any gradient that could guide faster behavior. A contrast emerges between formal timestamps and functional timing. While the system may record when a request is received and completed, those markers no longer influence behavior. Time exists as data, but not as an active constraint, allowing latency to expand without resistance. As operators align to this flattened timing structure, coordination begins to shift implicitly. Instead of synchronizing around real-time demand, actions cluster around delayed expectations. This creates a coordination pattern where delay is not only tolerated but anticipated. The absence of penalty ensures that earlier action does not produce a relative advantage. Completing a task sooner does not alter downstream outcomes or reduce future workload exposure. This eliminates incentive for temporal prioritization, reinforcing uniform delay behavior. Over time, the system develops a self-reinforcing backlog perception without a measurable backlog signal. Requests appear continuously pending, but none are marked as critically overdue due to attribution opacity. This diffuses urgency across all tasks, preventing escalation triggers from activating. A second-order effect emerges in how new requests are evaluated. Incoming tasks are immediately contextualized within an already delayed system, lowering the expectation of rapid handling. This pre-adjustment embeds delay at the moment of entry, accelerating propagation. As this pattern scales, small deferrals begin to synchronize across operators. Each operator independently delays, but the aggregate effect produces synchronized latency waves. These waves stabilize the system at a consistent delay interval, further hardening the equilibrium. The system now exhibits time horizon mismatch between formal rules and operational reality. Rules may define acceptable response windows, but actual behavior operates on extended, informal timelines. This divergence creates a dual system where only the delayed horizon governs behavior. Because no single delay can be isolated, feedback loops fail to form at the individual level. Without a feedback channel linking delay to consequence, operators cannot adjust behavior even if variation occurs. This locks the system into a non-corrective state. An analytical tension appears in whether reducing individual delay would change the system. Isolated faster responses do occur, but they are absorbed into the broader delayed structure without shifting it. This suggests that individual variation is insufficient to alter the equilibrium. As delayed timing becomes dominant, system throughput appears stable despite extended latency. Tasks continue to be completed, preserving the appearance of operational continuity. This masks the underlying shift from responsive processing to delayed completion cycles. The system begins to optimize implicitly for consistency of delay rather than minimization of delay. Uniform latency reduces variability, making outcomes more predictable within the delayed framework. This predictability reinforces the acceptability of high latency as a stable condition. A contrast emerges between variability and efficiency. While variability decreases, overall responsiveness deteriorates, yet the system favors the former due to its stability. This trade-off further entrenches the delayed equilibrium. As the delay baseline becomes rigid, attempts to accelerate responses encounter structural resistance. Faster actions disrupt coordination with other delayed processes, creating misalignment rather than improvement. This discourages deviation from the established latency pattern. Over time, the system's memory of faster response states erodes. New operational norms are formed entirely within the high latency environment. This removes reference points that could otherwise trigger corrective behavior. The equilibrium now operates as a closed loop where delay defines expectation, expectation defines behavior, and behavior reproduces delay. Each cycle reinforces the next without requiring additional external input. The system remains stable precisely because the incentive structure continues to sustain non-attributable delay. Under this equilibrium, the system no longer rewards faster response since early completion does not alter outcomes or reduce future exposure. Operators who act quickly receive no structural advantage, and their actions are absorbed into the same delayed processing cycle, limiting the incentive to deviate. At the same time, the system does not penalize extended delay because attribution remains diffuse and no individual action is isolated. Delayed responses carry no identifiable cost, allowing postponement to persist without triggering correction mechanisms. The effective reward shifts toward maintaining alignment with the delayed baseline rather than minimizing response time. Actions that match the prevailing latency integrate smoothly into the system, reinforcing consistency over responsiveness. In contrast, behaviors that attempt to operate outside this delayed structure introduce coordination friction without improving system outcomes. Deviation from the established timing pattern becomes operationally inefficient, narrowing the viable range of actions. The system stabilizes around a pattern where response timing is governed by incentive neutrality rather than urgency. Behavior converges on delay not as a failure to act, but as a rational response to a structure that neither recognizes nor differentiates